So when I first started my development career, I had no idea that there were actually tools out there that could help me identify problems in my software. However, many of these tools seemed really difficult to use, and they produced results that I struggled to make very much sense of. And so when I was preparing this talk, I kept those early struggles in the back of my mind. And my hope is today that if anybody in the audience has never profiled their code before, will have the confidence to go home and profile when they leave this room. So what does it mean to have performant UI? Performant UI is achieved when response and frame rate is consistent and quick enough that the human brain perceives it as fluid motion without lag or stutter. It's a whole lot more complicated than that, but this sums it up into one really oversimplified sentence. We've all experienced poor application performance where you're going along and things seem okay, and then suddenly it starts to lag and might even come to a halt. And users can be forgiving of this if it's a one-off that never happens. But if your application does this on a regular basis, be prepared for uninstalls and some really negative Play Store reviews. I don't want you to think that your app has to be so perfect that you never drop a frame here or there. We all know that software is never perfect, but your UI does have to operate smoothly enough that the brain can't perceive much, if any, difference in frame rate. So if your frame rate suddenly drops lower than what it was rendering at previously, for whatever reason, the user is going to experience what's called jank. Jank is also known by many other names. It describes unintentional pauses in motion. You might hear people say dropped or skipped frames, but what's really happening is that the user is seeing the same frame repeatedly, causing a noticeable hiccup in the animation. So in order to understand how jank happens, you need to understand a few terms first. Frame rate, or frames per second, is the frequency per second that your device's hardware can draw to a buffer. So I'll talk about buffering here in a moment, but for now just think of it as the number of times per second that a new image can be produced. Refresh rate is the number of times per second that your device's display can update. So refresh rate is measured in hertz, and 1 hertz is 1 cycle. So if we have a 60 hertz display, then we have a display that can update 60 times per second. So keep in mind that not all devices can even render at 60 frames per second. And even if they can, you aren't guaranteed to get exactly 60 frames. Even if you're doing all the right things. What's actually important is staying within those VSync ticks. So that begs the question then, what's VSync? VSync stands for vertical synchronization. It's like the pixel crossing guard, and it operates like a heartbeat. VSync is a way to ensure that your GPU's frame rate is in sync with your display's refresh rate. So if your frame rate is faster than your refresh rate, VSync throttles the frame rate so that you'll only be delivered new images when the VSync pulse occurs and says, "OK, go." So in order to better understand the role that VSync plays, then you need to understand, or at least have a basic understanding of how frame buffering works. So modern systems utilize at minimum what is known as double buffering, where your GPU composites the information it receives from the CPU and draws the image to a buffer frame. This buffer frame is commonly referred to as the back buffer. When VSync occurs, the image drawn on the back buffer gets flipped over to the front buffer, and that becomes the image that the user sees on the display now. So if for some reason your GPU is still doing work and on the back buffer, and it's not sitting around waiting for VSync to occur so that it can get swapped over to the front frame buffer, then that frame gets skipped, and the image that the buffer gets, the image that the user sees is that same image that they saw before for that interval, or for however many VSync intervals until that back buffer is done being drawn, and we'll see a new image on the next vsync occurrence. So Android actually utilizes triple buffering in Jelly Bean and Up, and it operates much like double buffering, except that we have potentially 2 back buffers to work with instead of 1 now. So in order to get an image on the screen, the CPU is responsible for updating a display list, and that gets handed off to the GPU to draw to a buffer. The GPU is also responsible for swapping these buffers so that the newly drawn image can be displayed when vsync says go. Now we already know that if the GPU isn't ready when vsync pulse happens and a frame is dropped and the same frame is shown again, since the entire rendering pipeline has to occur between vsync boundaries, if we do drop a frame and rendering crosses over that 16 millisecond threshold, then another frame buffer is allocated so that we can immediately start rendering the next frame without having to wait for that back buffer to become available. So here we have frame 0 displaying on the screen, and a vsync pulse happens. Frame 1 is now being displayed. However, frame 2 takes too long to render, and the GPU isn't done drawing to the back buffer. So at this point, we've skipped a frame, and a 3rd buffer is allocated, and we can start drawing to it immediately. So even though we already skipped a frame, hopefully now we can catch up and only drop 1 frame instead of always being behind and struggling to catch up. So what happens if vsync is turned off? If you play any games that benefit from a very fast frame rate, such as real-time first-person shooter games, you may have gone into your settings and turned off vsync. So what this effectively does is it disables that heartbeat that syncs up your GPU's buffer swap to your screen's refresh interval. The advantage to this is that your frames per second, your FPS is no longer capped at the display's refresh rate. The disadvantage now is that there's nothing to enforce when a frame swap or when a buffer swap happens, and so a swap can happen at any time. And this means that you could be in the middle of drawing a new frame. And when a buffer swap happens, you end up with what's known as screen tearing. And that's where you see part of the old frame and part of the new frame. So now that we know the basics of what causes jank, how do we avoid it? One of the best ways to avoid jank is just to simply avoid doing things that will knowingly contribute to rendering time, which might push you past those vsync boundaries. When optimizing your UI, one of the first things that you should look at is your view hierarchy. You want to have a shallow view tree and avoid deep nesting. So here's an example of a deeply nested layout. It's actually not that terrible. I'm sure you've seen worse. But there are a lot of useless view group parents in this that are serving zero purpose but have a negative impact on the performance by contributing to the measure and layout time required to render this list row. So notice here that the layout editor shows me a list of color-coordinated parent containers that wrap the selected image view. This helps to see the depth of the selected child view where the container views begin and end. So the image view that the red arrow is pointing to is wrapped with one relative layout and then 3 linear layouts, and that's completely unnecessary. This XML achieves the exact same results, but with a very shallow layout. So here's a side-by-side comparison of the design view screenshots for both layouts. The optimized layout on the right looks no different than the one on than the deeply nested on the left. But since this is a list row, our mistakes in the deeply nested layout get multiplied for every row displayed on the screen. Hierarchy Viewer is a great tool to give you an overview of your view tree structure. It can help you to quickly spot costly mistakes that contribute to rendering time. So to use Hierarchy Viewer, you need to follow the setup instructions that can be found on developer.android.com. But if you're using an emulator, then you're already good to go. To obtain a capture, just click on the Android icon to launch the DDMS Android device monitor, and then click on Hierarchy View Perspective if you're not already on it, and then select the process, or select your process on the Windows tab on the left. And you can either just double click it or click on the miniature blue tree icon to obtain a snapshot. So this is what a capture looks like. This is the tree overview of that deeply nested layout that I showed earlier. And in comparison, here's that flattened version. You can see there's a lot less going on. So Hierarchy Viewer also allows the option to get the relative measure layout and draw times for each view or view group. You can see that when I click on the icon with the 3 circles in the upper right-hand corner, the view I've selected shows how many milliseconds it took for measure, layout, and draw. And then also you'll notice that there's 3 dots that show up on each child view, giving you a quick visual of rendering performance, or what Hierarchy Viewer thinks it was. So clicking on the child view will give you the same detail view that you saw on its parent. However, just recently, as in like last night, I learned that, I learned from a very reliable source that these times are a lie. So I wouldn't rely on this feature at all. So as you can see here, when I click on the Recycler View node, there are 49 views, 48 child views plus the Recycler View itself. You can see how mistakes quickly add up. And then here's that flat layout. Now there's only 13 views, and some of the views were eliminated just by converting that text and heart icon into a single compound drawable. And the rest were eliminated by removing the extra depth created from the view groups that weren't serving any purpose. Again, I can't stress how important it is that because it's a Recycler View row, every mistake, or conversely optimization, is multiplied by the number of rows that are inflated. So it's important to choose the right view for the right job and know what the pros and cons are. For example, realize that you may have greater control over relative layout, but understand that that comes at an extra measure and layout. And the same goes with linear layout with the weight attribute. That extra flexibility comes to you at a cost. Now, in my deeply nested layout example, I know it seems completely contrived in this context, but it's really easy to actually end up with a view tree that looks very similar to that when you start reusing layouts with the includes tag. If you run Hierarchy Viewer, you'd quickly spot that mistake that might not have been so obvious until you saw the graph. If all you needed was a root view group, you can quickly, or you can remove those extra parents that are wasting time and space by swapping the root with the merge tag instead. The point is that understanding what you're putting on the screen and how you're doing it is critical. So to learn more about flat layouts and choosing the right view for the right job, if you haven't seen Window's talk on loving lean layouts, I suggest that you search for it on YouTube because it's pretty great. GPU Overdraw is a tool in developer settings that provides color-coded visual feedback to help you avoid drawing things that won't be seen on the screen. So when pixels are drawn over top of pixels, this is called overdraw. So in order to enable this feature, go into Developer Settings, scroll down to Debug GPU Overdraw, and then choose Show Overdraw Areas. The other feature is an accessibility feature for color blindness. And once you've enabled it, you'll see that you'll see the immediate effects of it. So scrolling through here, you see a lot of colors, especially shades of red, which are bad. You want to avoid red as much as possible. Light blue represents one layer of overdraw, or one layer beneath the layer that's visible. Light green is 2 layers. Light red is 3 times overdraw, so there's 3 layers underneath the layer you're actually seeing. And then dark red is 4 or more times overdraw, and you definitely want to look at what you're doing in that area. You can't completely avoid overdraw, but you want to minimize it as much as possible. And also, if there's no color, it means that there's no overdraw occurring at all. In my deeply nested layout, I was setting white backgrounds on all of the views. I don't need to do this for every single view. The white background is already defined in the app's theme, so the window will already have a white background. So even though this seems really obvious, extra backgrounds are actually a really common cause of overdraw. You can see here, just by removing all of the white backgrounds in the views that didn't need them, we've removed a lot of the overdraw. You may notice that in the upper left, the upper part of the cat images are darker than the lower part, and that's indicating an extra layer of overdraw. And that's because in my XML's image view, I was setting a source drawable for design preview purposes. If you plan to set the image in your Java code and you're only setting the drawable in XML simply for the preview, it's better to use the tools namespace instead of Android. So the Android system actually helps us out with overdraw by not drawing views that are completely hidden. But this won't work for views that are partially showing or custom views that override onDraw. For custom views that override the onDraw method, there's cliprect and quick-reject. Both are part of the Canvas API. Calling cliprect in your onDraw allows you to define the drawable's boundaries for a view. So anything that falls outside of this area will not be drawn, and then quick reject just returns true if the area is completely outside of the clipping rectangle. You've optimized as much as you think you can, and you're still experiencing jank. So now what? Profile GPU rendering is a great first place to look to get a holistic overview of UI rendering performance. To enable Profile GPU rendering, go into Settings, Developer Options, and then select Profile GPU Rendering option. There's two options. The first one is on screen as bars, and then the second one can be executed via command line for text output, or enabled here in Developer Settings to return graphical output to Android Studio monitors. Once you enable on-screen as bars, you'll see them appear immediately. An entire vertical bar represents the entire rendering pipeline, and each color is a phase of it. The green horizontal bar is the 16 millisecond reference bar, and if your vertical bar goes above that line, then things took too long. The orange section of the bar represents the time that the CPU is waiting on the GPU to finish its work. If this orange section gets tall, then that means too much work is happening on the GPU and the CPU is sitting around idle. The red section of the bar represents the time spent by Android's 2D renderer issuing commands to OpenGL to draw the display list. The blue and purple sections are only present on Android 4 and up. The purple section of the bar is the time spent transferring resources to the render thread, and then the blue section is the time spent creating and updating the display list. So if your bar is tall in this area, if the blue section is tall, you're likely doing too much work in your onDraw method. So on Marshmallows, the colors have been updated again. There's not really any documentation that I could find for that, but at least now there's labels next to it if you're looking in the Android Studio monitor. They still kind of correspond to the previous colors, but we have more granularity now in shades of green for things like measure and layout, animation, and input handling. Here's a side-by-side screenshot with Profile GPU rendering on screen as bars enabled and running on a Marshmallow device. On the left is the deeply nested, and then on the right is the optimized layout. And both are well above that 16 millisecond reference bar, but you can see here that by just eliminating the extra, the depth by the extra views or view groups in the hierarchy, we've significantly improved performance here. Android Studio has built-in monitors to help you quickly see performance in areas of network, GPU, CPU, and memory. So this video shows the GPU monitor in action. Much like profile GPU rendering on screen as bars, it displays the GPU rendering pipeline in colored sections and shows the green 16 millisecond reference bar. I find it easier to differentiate between the green colors using this monitor, plus you can zoom in on it, but it's a touch less convenient than the on-screen version. In order to run any of the monitors built into Android Studio, you have to turn on USB debugging and then set the debuggable flag in your Gradle build file. To capture GPU stats, you have to do one additional step, which is to go back to Profile GPU Rendering Developer option and then enable ADB shell dumps this graphics info. And lastly, if you're running on Android 5 or later, you'll need to turn on Enable View Attribute Inspection in Developer Settings. If you enable everything and you're still not getting output, then make sure that the DDMS device monitor is not running. So this screenshot displays memory, CPU, and GPU monitors running. The memory monitor at the top gives you a quick view of your memory pressure and roughly when garbage collection occurs. The dark blue at the top is the allocated space, and then the light blue is the free space. And then wherever you see it come up and then it just drops off, that's when a garbage collection happened. Systrace is a powerful tool for profiling UI performance. You can run it from Android Studio or via command line. I prefer command line, so that's what I'm going to show you. First, I changed directories to Android SDK Platform Tools Systrace directory, and then I ran this Python script. I set the number of seconds that I wanted Systrace to collect data to 10 seconds, and then I specified that I want the results output to a file named mytrace by using the -o tag. After that, I specified the options I wanted information about, so schedule, graphics view, and window manager. And you can see that you can see a full list because there's a lot more things that you can use Systrace to profile on at developer.android.com. Here's example output that was produced from the flattened layout with GPU overdraw remove. This is only showing the running apps process. The rest of it I've cropped out. When Systrace is running, it isn't just collecting a trace log of your app, it's also collecting system activity and other app events. So you probably want to kill other running apps before starting your trace. Here's a close-up of a single frame. This is what a happy frame looks like, where process, render, and update took less than 16 milliseconds. Most of the time here was spent on the render thread issuing draw commands, as can be seen by that light green bar labeled draw frame. The render thread will only be present on Android 5 and up. To navigate Systrace output, you can use ASDW, kind of like playing a game. A and D left and right, W is to zoom in, and S to zoom out. And then you can also use M to highlight a section or an entire frame. So if you don't see the purple vertical bars, on my display they show up purple, but here they're showing as blue. And if you want them to display, then you need to click on the View Options and then click on Highlight VSync in the upper right-hand corner. You'll see each frame represented as a colored dot, either green, yellow, or red. Green is good, and it means that process, rendering, and update with the new frame were all achieved in 16 milliseconds or less. Yellow means that you spent a little bit too much time, but you weren't too far past that 16 millisecond mark, so you probably maybe only dropped one frame. Red means that performance was poor and you took far too much time, and you might have dropped multiple frames as a result. So here in the highlighted area, I clicked on the section Draw on the UI thread, and then hit the M key to mark it. By clicking this section of the pipeline, Systrace will provide additional information about it. And I can also hold the Mac command key down to select multiple slices for inspection. So despite optimizing our layout and removing overdraw, we still have some performance problems, as can be seen by this red dot. The issue comes from the fact that the images are rather large and texture uploads to the GPU are expensive. Since these images are much larger than the images are actually drawn on the screen, a good optimization would be to resample these images so that we're pushing less pixels through the pipeline. Systrace tries to help us out by alerting us to issues. Here the alert says expensive bitmap uploads, and it provides us with more information about the problem. I already knew what the problem was because I intentionally created it for the purpose of this talk, and this alert is definitely on target. This information, even though it's generic, can sometimes prove useful just to point you in the right direction and help you to understand what part of the pipeline you need to focus on. And you can see these alerts at the top of your Systrace report as well. There's a row labeled alerts, and you can click on, or you can click on one of the red or yellow frame dots to see the alert for it. So in this talk, I didn't cover scaling, sampling, caching of bitmaps, threading, network performance, or memory management. We would be here for weeks. These are all extremely important items to consider, and they affect your app's UI performance. And you can certainly write your own code to handle all of these things, or you can lean on a trusted, well-tested library where these things have been taken into consideration for you. If you aren't using an image library, I recommend you use one instead of reinventing the wheel. There's Glide, Fresco, and Picasso, to name a few. But having said that, using an image library is not a silver bullet, and now suddenly all of your problems are solved. If you continue to experience performance issues, it means it's time to start profiling. And again, my goal today was to inspire you to profile and optimize your app. And I hope that if you haven't already, you'll go home and do it today. Thank you. My favorite library was the question, image library. I have used Picasso a lot, but I have been using Glide a lot more recently. And I haven't used Fresco, but it looks really interesting. I've looked at the docs, and so my next project, I might give that one a go. Okay, well, if there are no more questions, thank you.